Consequences of the theory of Einstein Relativity and its experimental evidence. Einstein proved that gravity is not a force, but it is a geometric of space-time fabric. And time is not absolute, but relative with gravity. In presence of matter and energy, space-time like fabric bend, twist, wrap, even ripple. He also gave field equations set to quantify the cosmic curve. And output of this theory was a complete new concept, which is the base of our present modern science. That matter and energy tell space-time how to bend, and the bending of space-time tells matter how to move. But the journey was not so easy. Max Planck, the great physicist at that time, once tried to discourage Albert Einstein from working on a new theory of gravity. Mr. Planck told Einstein, "As an older friend, I must advise you against it, for in the first place, you will not succeed. And even if you succeed, no one will believe you." But Einstein was Einstein. He tried for 7 years to understand the fabric of cosmos and finally succeed to find the complete field equation called Einstein field equation. The theory and its field equation was so complex that even famous physicists at that time were not able to understand the theory of relativity. There is a famous quote right back from the early days of general relativity around 1919. Arthur Eddington was giving a lecture and someone said, "Professor Eddington, you must be one of the 3 persons in the world who understand general relativity." Eddington then sat in silence for a while before the original person said, "Don't be modest, Eddington." Finally, Eddington picked up on the contrary. "I'm trying to think who the 3rd person is." This film is based on Consequences of Einstein's theory of relativity and the experiment's evidence. Myself, Tamanna Pradhan, stay with me to understand each of them. Please subscribe, like, and share my video. Your support will be my inspiration. Gravitational time dilation. Gravitational time dilation is a form of time dilation in which an actual difference of elapsed time between 2 events as measured by observers situated at varying distances from a gravitating mass. The practical applications of gravitational time dilation is GPS. Present day, a global positioning satellite system or GPS are provided in all luxurious cars. GPS receiver attempts to find signals from at least 3 satellites to coordinate your position. The GPS satellites send out timed radio signals that the receiver listens to, and triangulating its position is based on the travel time of the signals. The challenge is the atomic clocks on the GPS are running faster than atomic clocks on Earth, creating timing issues. So, Engineers need to make the clocks on a GPS tick slower because the GPS satellites are staying above Earth and experiencing weaker gravity. Even though the GPS satellites are moving and experience a 7 microsecond slowing every day because of their movement due to special relativity. Again, due to general relativity, weaker gravity in Earth orbit causes the clock to tick about 45 microseconds faster than a ground-based clock. Adding the two together results in the GPS satellite clock ticking faster than a ground-based clock by about 38 microseconds daily. This sounds small, but the high precision required of the GPS system requires nanosecond accuracy, and 38 microseconds is 38,000 nanoseconds. If these effects were not properly taken into account, a navigational fix based on the GPS constellation would be false after only 2 minutes, and errors in global positioning would continue to accumulate at a rate of about 10 kilometers each day. The whole system would be utterly worthless for navigation in a very short time. One of the most important tests is gravitational lensing has been observed in distant astrophysical sources, which is predicted by general relativity. The most precise tests are analogous to Eddington's 1919 experiment. Sir Arthur Stanley Eddington, an English astronomer, physicist, and mathematician, philosopher of science, and a popularizer of science. The first observation of light deflection was performed by Arthur Eddington and his collaborators during the total solar eclipse of May 29, 1919. Noting the change in position of stars as they passed near the Sun on the celestial sphere. When the stars near the Sun at that time in the constellation Taurus could be observed. Observations were made simultaneously in the cities of Sobral, Serra, Brazil, and in west coast of Africa. The result was considered spectacular news and made the front page of most major newspapers. It made Einstein and his theory of general relativity world famous. The measurement was repeated by a team from the Observatory in the 1922 eclipse, with the results that agreed with the 1919 results, and has been repeated several times since, most notably in 1953 by Yerkes Observatory astronomers and in 1973 by a team from the University of Texas. A quasar is an excellent example of gravitational lensing. The quasar is about 8 billion light years from Earth and sits behind a galaxy that is 400 million light years away. 4 images of the quasar appear around the galaxy because the intense gravity of the galaxy bends the light coming from the quasar. Another consequence of general relativity is gravitational redshift. Let us know that is gravitational redshift and how it is related to general relativity. The gravitational redshift is a simple consequence of Einstein's equivalence principle and was found by Einstein 8 years before the full theory of relativity. The gravitational redshift is the phenomenon that clocks deeper in a gravitational well tick slower when observed from outside the well. More specifically, the term refers to the shift of wavelength. The red side in an optical spectrum when observed from a point at a higher gravitational potential. In the latter case, the clock is the frequency of the photon, and a lower frequency is the same as a longer wavelength. To understand it more deeply, let us discuss what Doppler effect is. Christian Andreas Doppler, who was an Austrian mathematician and physicist, he gave a principle called as the Doppler effect, that the observed frequency of a wave depends on the relative speed of the source and the observer. He used this concept to explain the color of binary stars. A common example of Doppler shift is the change of pitch heard when a vehicle sounding a horn approaches and recedes from an observer. Compared to the emitted frequency, the received frequency is higher during the approach, identically at the instant of passing by, and lower during the recession. The reason for the Doppler effect is that when the source of the waves is moving towards the observer, each successive wave crest is emitted from a position closer to the observer than the crest of the previous wave. Therefore, each wave takes slightly less time to reach the observer than the previous wave. And it is same in case of light, the shift of wavelength of a photon of a longer wavelength. The red side in an optical spectrum when observed from a point at a higher gravitational potential. Walter Sidney Adams, an American astronomer, gold medalist of the Royal Astronomical Society, identified the effect in the spectral lines of the star Sirius A in 1925. Then in 1954, the first accurate measurement of the gravitational redshift of a white dwarf was done by Popper, measuring a 21 km per second gravitational redshift of 40 Erdani b. Again, the redshift of Sirius B was finally measured by Greenstein in 1971, obtaining the value for the gravitational redshift of 89 plus minus 19 km per second. With more accurate measurements by the Hubble Space Telescope showing 80.4 plus minus 4.8 km per second. Gravitational redshift and light from the S2 star orbiting the supermassive black hole Sagittarius A in our center of the Milky Way has been measured with the Very Large Telescope using gravity, NACO, and Symphony instruments. The Pound-Rebka Experiment. Robert Pound and Glennie Rebka Jr. in 1959 measured the change of frequency of light moving in a gravitational field. That was an experiment in which gamma rays were emitted from the top of a tower and measured by a receiver at the bottom of the tower. The purpose of the experiment was to test Albert Einstein's theory of general relativity by showing that photons gain energy when traveling toward a gravitational source. In this experiment, the frequency shift was a blue shift toward a higher frequency. Equivalently, the test demonstrated the general relativity prediction that clocks should run at different rates and different places in a gravitational field. A very accurate gravitational redshift experiment was performed in 1976, where a hydrogen maser clock on a rocket was launched to a height of 10,000 kilometers, and its rate compared with an identical clock on the ground. It tested the gravitational redshift to 0.007% and found Einstein true. Shapiro time delay or light travel time delay testing. It is sometimes called the fourth classical test of general relativity. The gravitational time delay effect was first predicted in 1964 by Irvin Shapiro due to general relativity. Irvin Ira Shapiro, PhD in physics from Harvard University, an American astrophysicist and Time-Ken University professor at Harvard University. He was also director of the Harvard-Smithsonian Center for Astrophysicists Tested General Relativity. The Shapiro time delay effect or gravitational time delay effect is one of the four classic solar system tests of general relativity. That was, bounce radar beams off the surface of Venus and Mercury and measure the round-trip travel time. When the Earth, Sun, and Venus are most favorably aligned, Shapiro showed that the expected time delay due to the presence of the Sun of a radar signal traveling from the Earth to Venus and back would be about 200 microseconds with ERA technology. That because radar signals passing near a massive object take slightly longer to travel to a target and longer to return than they would if the mass of the object were not present. The time delay is caused by space-time dilation, which increases the path length. Another prediction of general relativity is gravitational wave. Gravitational waves are disturbances in the curvature of space-time, generated by accelerated masses that propagate as waves outward from their source at the speed of light. They were proposed by Henry Poincaré in 1905 and subsequently predicted in 1916 by Albert Einstein on the basis of his general theory of relativity. Massive objects like stars stretch and curve this cosmic fabric. Gravitational waves affect this fabric as well, causing ripple-like distortions. Previous studies have confirmed the existence of gravitational waves, which are generated by the acceleration or deceleration of massive objects through indirect methods. In 1993, Russell A. Halsey and Joseph H. Taylor Jr. received the Nobel Prize in Physics for the discovery and observation of Halsey-Taylor binary pulsar, which offered the first indirect evidence of the existence of gravitational waves. In 2014, scientists announced that they had detected gravitational waves left over from the Big Bang using the background imaging of Cosmic Extragalactic Polarization Telescope in Antarctica. It is thought that such waves are embedded in the cosmic microwave background. However, further research revealed that their data was contaminated by dust in the line of sight. But the LIGO find is the first direct detection of this enigmatic phenomenon. The first confirmed gravitational wave on September 14, 2015. LIGO, Laser Interferometer Gravitational Wave Observatory. It is a joint project operated by the California Institute of Technology and the Massachusetts Institute of Technology and funded by the National Science Foundation. Astrophysicists Kip Thorne and Barry Barish of Caltech and Rainier Weiss of MIT won the Nobel Prize for Physics for the first detection of gravitational waves. The first detection was so large that according to LIGO spokesperson Gabriela Gonzalez, it took the team several months of analyzation to convince themselves that it was a real signal and not a glitch. Researchers said the collision occurred 1.3 billion years ago between two black holes that were about 29 and 36 times more massive than the Sun, respectively. During the crash, about 3 times the mass of the Sun was converted into gravitational waves in less than a second, generating a peak power output of about 50 times that of the entire visible universe. A second signal was spotted on December 26 of the same year. Finally, after several months, the official news of the detection of gravitational waves was given at a press conference on 11 February 2016, after the team had announced the most important scientific news so far this century. Gravitational waves were detected after 60 years of searching and 100 years since the prediction of their existence. The detection is a milestone moment in astronomy and astrophysics. According to LIGO researchers, unlike light waves, gravitational waves don't get distorted or alerted by interactions with matter. As they race through space, they therefore carry pure information about the objects and events that created them. A gravitational wave detector project on Indian soil. India planned to make an advanced gravitational wave observatory, which will be located in India as part of the worldwide network. LIGO-India is a multidisciplinary mega science project that requires expertise from a variety of fields as laser, vacuum, optics, computer, etc., and of course physics, and provides research opportunities. LIGO-India received the Indian government's in-principle approval in February 2016. Since then, the project reached several milestones towards selecting and acquiring a site and building the observatory. The LIGO-India project will be built by the Department of Atomic Energy (DAE) and the Department of Science and Technology (DST), Government of India, with a Memorandum of Understanding with the National Science Foundation (USA), along with several national and international research and academic institutions. The project is being led by 4 institutions. Planet Mercury. The evidence came from the planet Mercury in the 19th century. It was found that Mercury does not return to exactly the same spot every time when it completes its elliptical orbit. Newton's law of gravity could not explain this perihelion shift, but general relativity gave the correct orbit. As seen from Earth, the precession of Mercury's orbit is measured to be 5,600 seconds of arc per century. 1 second of arc equals to 1 by 3,600 degrees. Newton's equations, taking into account all the effects from the other planets, as well as a very slight deformation of the Sun due to its rotation, and the fact that the Earth is not an inertial frame of reference, predicts a precession of 5,557 seconds of arc per century. There is a discrepancy of 43 seconds of arc per century. Einstein was able to predict without any adjustment whatsoever that the orbit of Mercury should persist by an extra 43 seconds of arc per century proved general theory of relativity correct. And Einstein's theory was an explanation for the 43 per century precession of the perihelion of Mercury. According to general relativity, mass bends the space, and in a curved space-time, a planet does not orbit the Sun in a static elliptical orbit, as in Newton's theory. Rather, the orbit is oblique to the curvature of space-time. When Einstein calculated the magnitude of this effect for Mercury, he got precisely the previously unexplained 43 seconds. He correctly took the view that this was an important confirmation of his theory. The joint European-Japanese Bepi-Colombo mission will send 2 probes to orbit Mercury, allowing for far more accurate measurements of its motion. We'll hope that the measurement will confirm his predictions. In fact, there are several instances of relativity that we can see in our daily lives, and even technologies we use today that demonstrate that Einstein was right. But the most concrete evidence of general relativity in astronomical physics is black holes. Black holes, the most magical and weird cosmic object, in which may have the secret of creation of universe, or a secret path to journey for hyperspace or multiverse, or which can explain the space-time which is predicted from general relativity. A black hole is a region of space-time where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light cannot escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of the gas collide with each other more and more frequently, and at greater and greater speeds, the gas heats up. Eventually, the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but instead coalesce to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction, and the gas stops contracting. It is a bit like a balloon where there is a balance between the pressure of the air inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars remain stable like this for a long time with heat from the nuclear reactions balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fuels. Paradoxically, the more fuel a star starts off with, the sooner it runs out. This is because the more massive the star is, the hotter it needs to balance its gravitational attraction. And the hotter it is, the faster it will use up its fuel. Our sun has probably got enough fuel for another 5,000 million years or so, but more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. When a star runs out of fuel, it starts to cool off and so to contract. What might happen to it then? It will become a black hole. Coming episode, I will make a complete video about black holes, but in this episode, we will only discuss about its evidence and proof of general relativity. John Michell, 25th December 1724 to 21st April 1793, was an English natural philosopher who provided pioneering insights into a wide range of scientific fields, including astronomy, geology, optics, and gravitation. He was one of the greatest unsung scientists of all time, who was the first person known to propose the existence of black holes. Michell suggested that there might be a large number of stars like this, although we would not be able to see them because the light from them would not reach us. We would still feel their gravitational attraction. Such objects are what we now call black holes, because that is what they are, black voids in space. He told that there might be an object massive enough to have an escape velocity greater than the speed of light. 1796, Simon Laplace predicted the existence of black holes. It is therefore possible that the largest luminous bodies in the universe may through this cause be invisible. But by Einstein's general relativity, successfully prediction of black hole came due to space-time curved by gravity. 1916, Karl Schwarzschild used Einstein's theory of general relativity to define a black hole. Defined gravitational radius of black holes, later called the Schwarzschild radius. 1935, Subramanian Chandrasekhar, pioneer in theory of white dwarfs that led to an understanding of mass limits that decide whether a star will die as a white dwarf, neutron star, or black hole. 1964, John Wheeler coined the term black hole. John Archibald Wheeler, July 9, 1911 to April 13, 2008, was an American theoretical physicist, doctorate at Johns Hopkins University, and in early 1950s he associated with design and build the hydrogen bomb. He was professor of physics at Princeton University, which he joined in 1938, remaining until his retirement in 1976. At Princeton, he supervised 46 PhDs, more than any other professor in the Princeton physics department. He worked with Niels Bohr in explaining the basic principles behind nuclear fission, together with Gregory Brett. He is best known for using the term black hole. In 1969, he gave a graphic description of an idea of black holes. John Wheeler's thinking was if light is both wave and particle. He coined that under the theory that light is made up of waves. It was not clear how it would respond to gravity. But if light is composed of particles, one might expect them to be affected by gravity in the same way that cannonballs, rockets, and planets are. A cannonball fired upward from the Earth will be slowed down by gravity and will eventually stop and fall back. Then a photon particle, which is called as light, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? Then in 1915, Einstein proposed general relativity, which predicted there must be a supermassive object who will be responsible for gravity, due to its excessive curve in space-time to hold the entire galaxy. Stephen Hawking, Professor of Mathematics at the University of Cambridge. 8 January 1942 to 14 March 2018, was an English theoretical physicist, cosmologist, and author who director of research at the Center for Theoretical Cosmology at the University of Cambridge at the time of his death, who defined modern theory of black holes, which describes the final fate of black holes. 1970, Sinus X1, the first good black hole candidate that astronomers found. It emits X-rays and has a companion smaller than Earth, but with a mass greater than that of a neutron star. 1994, Hubble Space Telescope provides best evidence to date of supermassive black holes that lurk in the center of some galaxies. The Space Telescope Imaging Spectrograph (STIS) revealed large orbiting velocities around the nucleus of these galaxies, suggesting a huge mass inside a very small region. There is a very famous talk between Einstein and Charlie Chaplin. When Albert Einstein met Charlie Chaplin, Einstein said, "What I most admire about your art is its universality. You do not say a word, yet the whole world understands you." "It's true," replied Charlie Chaplin. "But your fame is even greater. The world admires you, but nobody understands you." And for this, Einstein theory was experimented time to time, but every time found Einstein general relativity true. In the coming video, I will be making a full documentary about how this universe is created. Till now, thanks for watching my video.